Okay, who's been here? Where is that? What is that? Yeah, St. Louis Arch. Okay, I think it was built in the 1960s, designed by Eero Saarinen, something like that. But what it is supposed to represent is St. Louis was the gateway to the West. I think Lewis and Clark started their expeditions from there. But the relevance for us here is the shape of this arch. This arch kind of suspends itself. It just stands up. You can take an elevator ride up here. It's pretty high. Nothing in the city of St. Louis is supposed to be taller than that gateway arch. But this gateway arch requires that you use a hyperbolic cosine. So we're going to introduce that. That's our new function for this section. And let me give you some definitions for these hyperbolic sines and hyperbolic cosines. So this is section 5.9. Hyperbolic sine looks like this. Sine, and then you've got that h, because it's no longer just the regular sine and cosine that are functions of the unit circle that you're used to. They're hyperbolics. These are functions of hyperbolas, the unit hyperbola, not the unit circle. And it's e to the x minus e to the negative x over 2. Or, of course, you could write that as 1/2 e to the x minus e to the negative x. A hyperbolic cosine is e to the x plus e to the negative x over 2. Or again, likewise, half of this. And those are the two that you need. The rest of these things follow from what you would guess in terms of your laws of trigonometry. That is, the tangent, hyperbolic tangent, is the sine over the cosine. Well, if I did the sine over the cosine, these 1/2s are going to cancel out. So I'd be left with e to the x minus e to the negative x over e to the x plus e to the negative x. So that's your hyperbolic tangent. You can get other functions as well. If I wanted the hyperbolic cosecant, I'd simply do 1 over the hyperbolic sine. So 1 over the hyperbolic sine. Now let me share with you a little convenience that people use for some of these functions. Hyperbolic cosine, boy, that sounds like kind of a mouthful. So a lot of times we just call it Cosh, right? I mean, it's what it looks like, Cosh. And for reasons that go beyond me, and I don't know whose imagination it was, they call that cinch. I know there's no CH there, but it's Cosh and cinch. So it's a little bit convenient. If you want to use it, great. If not, oh well. Likewise, you can get the hyperbolic cotangent by taking the reciprocal of the hyperbolic tangent, etc. One thing that you can see from this is some work with our derivatives. If I differentiate d by dx, the hyperbolic sine, that's the derivative of 1/2 of e to the x minus e to the negative x. Well, the 1/2 is just a constant, so we can ignore that. So it's 1/2. What's the derivative of e to the x? E to the x. So, all right, that's pretty easy. E to the x. What happens when I differentiate e to the negative x? Negative e to the negative x. So that negative is going to cancel with this one. So the derivative of a hyperbolic sine is what? Hyperbolic cosine. It's your Cosh. And symmetrically, derivative of Cosh is sinh. The nice thing about these hyperbolic functions in terms of the sine or the cosine is that there's no negative that you have to worry about. Remember when you differentiate cosine, derivative of cosine gives you that annoying negative. It's not sine, it's negative sign. It's just the way it works out. But here, we don't have to worry about that. If you want to have a little bit more of an understanding of these functions, you can look at this graph right here. So our unit circle helped us define our trig functions. Our unit circle was this one, x squared plus y squared equals 1. And from that, you got a basic identity, cosine squared plus sine squared equals 1. Kind of like the foundation for all of our trig identities. Well, with the hyperbolics, we're going to work with not the unit circle, but the unit hyperbola. So instead of having points on the unit circle, you're going to have points on the unit hyperbola. And I've got one branch of the hyperbola shown here, but your points have coordinates of Cosh and sinh. That also turns into an identity. Now there's a lot of identities that you can learn and use and derive in this section. Let me be very clear. I want you to know exactly one of them. So I'm not going to assail you with tons of them. This is the one that I expect you to know. So hyperbolic cosine squared or Cosh squared minus sinh squared equals 1. That's the one identity that I want you to know. You can get and prove more identities based on this one, but this is the one that you should know. Like I said, I'm not going to go crazy on these things. I will show you how to work with this. We'll do one example. So, it's kind of like the foundational one. You can get everything from this. Back when you took trig, this identity, cosine squared plus sine squared equals 1. I mean, you can get everything from there in terms of your identities. You can get the half angle formulas, you can get the double angle formulas, you can get other versions of this. If I were to take this and divide everything through by, say, cosine squared of theta, then I get a new identity. I get 1 plus tangent squared of theta equals secant squared of theta. And so now I got a new identity. So just so much can follow from that one identity that it's the one that I choose to have you know. We'll also use it in one of our integration problems. So appreciate the question. Like I said, problem number 8 asks us to establish an identity. And it's kind of what I just did for our trig identity. We've got hyperbolic cotangent squared minus hyperbolic cosecant squared equals 1. So problem number 8, cotangent h squared of x minus cosecant h squared of x equals 1. Let's see if we can't establish this identity somehow. Well, I guess what I'm going to rely on is the one that I have memorized. That's this one. Let's take a peek at the left-hand side of this. The left-hand side of this has things like cotangent squared and cosecant squared, or hyperbolic cotangent squared. Hyperbolic cotangent is really the ratio of two functions. Cosine over sine. Yeah. So this is Cosh squared over sinh squared. Sinh squared. And this is 1 over sinh squared. So, okay, that's kind of suggestive here. So let's see if we can't play around with this a little bit and make things happen. If you're being really formal and true to things, then you should probably only work with one side. What's nice in rewriting it like this is that I can see I've got common denominators. So this is cosh squared of x minus 1 over sinh squared. Now let's look at the numerator. And here's where it's helpful that we have this one memorized. If I rearrange this, if I move the sinh squared over here and the 1 over here, I can rearrange this as cosh squared of t minus 1 equals sinh squared. Yeah, so essentially what's going to happen here is I can replace this numerator, right? What's that numerator? Sinh squared over sinh squared. And sinh squared over sinh squared is 1. So, just working with the left-hand side, I showed that the left-hand side equals the right-hand side. And that's what you're asked to do here, is to establish that identity. Okay, but let's work with some other things in this section, not just establishing identities. That's a low priority for me with regards to this section. Let's do a little practice with the derivatives first. So you should have a handout with some rules of differentiation for your hyperbolics. The ones that I really want you to know are the basic ones right here. This one, and this one. So those three. I mean, some of these other ones should look familiar from your work with trigonometry and your work in Calc 1. But it's these that are really going to get most of our work done. Those are mostly what you're going to see. The reason that the hyperbolics aren't quite as useful as their trigonometric cousins is they're not periodic. When you're working on the unit circle, after a while you come back to the same point. You get this periodicity. The sine function repeats itself after a while. Same with the cosine, same with the tangent, all our trig functions. That's not true with the hyperbolics. Once you go out here, you don't come back. It doesn't repeat itself. Bless you. All right, so keep this handy, keep it to one side. Let's work with some trig functions or some hyperbolic functions and differentiate them. Don't forget our usual rules of the product rule, the quotient rule, those still apply. We'll start with problem number 24 I should say. F of x is the hyperbolic cosine or cosh of 8x plus 1. 8x plus 1. Sorry, let me rewrite that. Cosh of 8x plus 1. Now, I mentioned something earlier, kind of by way of review / warning. Let me repeat myself, or repeat that idea here. This is not something for which you use the product rule. You can't differentiate cosh times this and then derivative of this times cosh. Don't do that. This is chain rule. You've got an outside function and an inside function. So the derivative of the outside, derivative of cosh, is what? Good. Sinh, sine h. So sinh of 8x plus 1 times what? 8, which is the derivative of the inside. Great. And that's it, really, other than just cleaning it up. If you want, put the 8 out in front. 8 sinh of 8x plus 1. Not sure why I want to leave that 8 out of there, but I do. Let's try another one, unless there's some questions on this one. Please make sure you don't differentiate this using the product rule. All right. Problem number 28. Y equals the ln of hyperbolic tangent of x over 2. Now, kind of a quick reminder here for us. d by dx ln of u. When I differentiate the logarithm, what do I get? 1 over u times the derivative of the inside, so times du by dx. Derivative of the outside times the derivative of the inside. So 1 over u du dx. So the same thing is going to be true here. My u in this case is the whole thing. So it's going to be 1 over hyperbolic tangent of x over 2 times the derivative of this whole thing. Wow, this is the problem that keeps on giving, right? Because then we go to the derivative of the hyperbolic tangent. And you can take a look at your sheets there. What's the derivative of the hyperbolic tangent? Thank you. Hyperbolic secant squared. So this is still here. 1 over the hyperbolic tangent. Hyperbolic secant squared. But am I done? No. Good. Someone else. Someone else that I haven't heard from yet today. What else do I have to include here? I differentiated the outside. I got secant squared. Hyperbolic secant squared. Go ahead. Yeah, chain rule. Times the derivative of the inside. What's the derivative of x over 2? Come on. Derivative of x over 2. 1/2.
That was easy.
Yes. Cool. So 1/2. Thank you. That may or may not clean up some. I'm just going to clean it up this way. We'll put this up here. Actually, it would clean up some. I'm not sure how much I want to spend, effort I want to spend. 1/2 times, what do you want to call it, sech? Hyperbolic secant squared over tanh of x over 2. You would get some simplification here because there's a Cosh term that could cancel out, but you know what? I don't want to get too mired in the algebra here. Let's just leave it like this. That's a reasonable place to leave it. Okay. One more kind of along this lines, and it's an important one because, again, there's some confusion on the notation. Just like people want to use the product rule here, you can't. You got to use a chain rule. So there's also some confusion on problems like number 32. So g of x is hyperbolic secant squared of 3x. The thing you have to realize about this is that this is just some notation. It's a convenient way to write hyperbolic secant of 3x in parentheses squared. So, cool. What I want you to do is I want you to find the derivative of that. So, let's see. Oh yeah, let's go back to our high-tech pause button. So, cool. At home, fast forward this until that disappears. I'm going to continue learning your names and work on that derivative. still, oh, okay, we still got sound. That's good. Okay, so this is another chain rule problem. What's the outside function in this case? The squared function. So derivative here is going to be 2 times hyperbolic secant of 3x to the first power times the derivative of the inside. Sech of 3x. So let's work on this one. So that's 2 hyperbolic secant of 3x. What's the derivative of the hyperbolic secant? Yep. So it's negative, I'll put this in parentheses or brackets like this, negative of the hyperbolic tangent of 3x times the hyperbolic secant of 3x times the hyperbolic tangent of 3x times what? 3. Good, because you got to use the chain rule yet again here. Putting this all together, if you notice we've got constants here, here, and here. What's all going to come out in front? -6. And then we can make our lives a little bit easier because we got hyperbolic secant twice. So I'll just write that as hyperbolic secant squared of 3x times hyperbolic tangent of 3x. Whew. Get the oxygen bottle. All right. How's that one looking? They're going to take some practice, but I think can help you get used to them. Let's do something that hopefully you're comfortable with, and that is finding the equation of a tangent line. So anything on problem 32 before I move on to problem number 36? All right. Let's see. Okay, so our function in problem number 36 is e to the cosine of x. Or e to the hyperbolic cosine of x, I think. Nope, hyperbolic sine. There we go. Y equals e to the hyperbolic sine of x. And we want the equation of the tangent line through the point 0, 1. So there's a couple things you're going to need in order to find the equation of the tangent line. One is the point. They've given you the point. Actually, they're fairly generous. This is one place that I think I'd be a little bit more demanding than the book. It is, they gave you the x and y coordinates. I'm just going to give you the x coordinate. I'll tell you that right now. I think you should be able to find the y coordinate. But that's not that hard. E to the sine h of 0. Well, that's going to be e to the 0, which is 1. I'm hoping that you can find the y coordinate there. We'll go back after this and play with how you can actually find these values from our calculator. Let's see here. So what else do I need? I've got a point. What's the last ingredient I need to find the equation of a tangent line? Yeah, slope. I need the slope of the tangent line. So the derivative here, dy by dx, is going to be e to the sinh of x times what? It's e to the, so the rule here is, let's see, where is it? There you go. Derivative of e to the u is e to the u times the derivative of the exponent. So what's the derivative of the exponent here? Yes. So d by dx of sinh of x is cosh of x. E to the sinh of x times cosh of x. So that's our slope, dy by dx. I'm going to need to evaluate that at x equals 0. So that's going to be e to the sine h of 0 times cosh of 0, which is going to be e to the 0 times 1. If you're curious where these numbers are coming from, they're coming from the definition of sinh and cosh. Cosh of 0 would be e to the 0, which is 1, plus e to the 0, which is 1 again. 1 plus 1 is 2, divided by 2 is 1. And likewise over here, sinh of 0 is just going to be 0. So there's your slope. We've got our slope, we've got our point. Y minus y1 equals m times x minus x1. I sincerely hope that one's memorized. 0, 1 is your x1, y1, and the slope is 1. Y minus 1 equals 1 times x minus 0. So y equals x minus 1. Yay! There's your tangent line. Now, it's helpful if you keep in mind the basic definitions of some of these things, but I don't expect that. So, is it x plus 1? Thank you. I don't expect you to keep in mind the basic definitions and evaluate these things using the basic definitions. So what I do expect is that you can get some values from your calculator. So let's practice that here. And we'll do a few examples. So suppose I wanted the hyperbolic sine of 4. If you look back at old exams, sometimes I'll ask questions, not maybe this one, but something similar. Now, longhand, this would be e to the 4 minus e to the negative 4 over 2. I really don't feel like evaluating that by hand. So let's let our calculator do it. To find that on your calculator, hit the second key, then the catalog key. We got to scroll a long ways down. But let me show you a shortcut. I don't feel like scrolling all the way down to the S's. We've only got so much time. So the shortcut is just to type the first letter, which is an S. Now, you know you can type the S because you've got this little A up here. That character says, all right, if you type something, it's just going to jump down to the S's. So the S is right above the LN key. You press that once, you notice it jumps down to the beginning of the S's. And let's just scroll down a little bit further until you see the hyperbolic sine. So sine, sine inverse, hyperbolic sine. There you go. Hyperbolic sine of 4. There you go. Cool. Catalog is right above the 0. So you have to hit the second button and then the 0 to get catalog. Now, here's kind of a freebie. We've all got this on our calculator. What if I asked you for the hyperbolic cosecant of 4? Are you going to take and plug in, all right, that's going to be 2 over 4, e to the 4 minus e to the negative 4? Or is there a smarter way to do this one? Yeah. It's going to be 1 over the hyperbolic sine of 4. So, here's the cool thing that you can do. You've already got this here. Let's hit 1 divided by our previous answer. So hit the second button, and then this key, see it says A and S, and that's your previous answer. So it's going to take 1 divided by that. In a similar way, I could have also just hit the X inverse key. X inverse key is going to take the reciprocal of my previous answer, and I should get back to where I started. So hopefully you can use some of these tricks to get some of these other values. Let's try one more, or maybe a couple more like this. Let's try the hyperbolic tangent of 2. See if you can't find this one. These aren't problems in the book. That's why I just put EX there. That's my shorthand for, all right, this is my own example. So again, go to the catalog, second, 0. To jump down to the t's, what button should I push? 4. If you notice, right above the 4 up to the right, there's the letter T. So you jump down to the T and don't have too far to go. Hyperbolic tangent. I want the hyperbolic tangent of 2. 0.96. Nice. So maybe a couple easy points on this one. If I put something like this on an exam, 0.964, etc. Quite often I'll ask you to round to a specific variable. In this case, suppose I ask you to round to the nearest 10,000th place. So that's the 4th decimal digit. So this would be approximately 0.964. Do I need to write the 0? If I'm asking you to round to the 10,000th place, there should be something there. So, because otherwise it looks like you just rounded it to the 1,000th place, right? So there has to be a 0 there to let somebody know that, yeah, I did take care of the digits all the way down to the 10,000th place. It's not just left off. So put the 0 there. Are you okay with these hyperbolics, finding the actual number values off your calculator? Okay. Let's continue then. Let's do a few more. Maybe we'll start doing some integration problems. So, we'll start with problem number 46. So the integral of Cosh of the square root of x over the square root of x. Okay, so, boy, if this was just a simple Cosh function, I could integrate it. Because we know that Cosh is the derivative of sinh, so I could find the antiderivative pretty easily. But unfortunately, I've got this square root of x term here. Now, what's unusual about this one, and this is a little tricky, is the way that the U substitution will work. So let me just show it to you in this particular case. If I was to write the square root of x with exponents, it'd be x to what power? 1/2. So du by dx would be 1/2 x to the negative 1/2, or better yet, 1 over 2x to the 1/2. And x to the 1/2 can be rewritten as 1 over 2 square roots of x. Okay. Multiply both sides of this by dx, the differential. I get du equals dx over 2 square roots of x. And I'm coming pretty close to what I have in the integrand. In the integrand, I've got Cosh of the square root of x and dx over the square root of x. So just kind of writing it a little bit different. What's the difference between what I've got here and what I've got here? The 2. So let's get rid of the 2. I can multiply both sides by 2. Two du is dx over the square root of x. Perfect. This and this are identical, so I can make a direct use substitution. That's the way I like doing these things. You don't have to do it the same way. That's okay. This gives me a nice 2u, or just give me 2du. The 2 can come out in front. Now you got to ask yourself, well, what do I differentiate to get Cosh? Andrew, see? Look at your sheets. So now, what do you differentiate to get Cosh? Sinh, yeah. So that's 2 of sinh plus your constant. And u was the square root of x. So that's it. There's your final answer. Now, I'm not trying to do any cheap advertisements, but something that's kind of handy for you is something called Wolfram Alpha. Yeah, there you go. Wolfram Alpha. Yeah, say that 10 times fast. And you can try and check a lot of your answers that way. It's not a bad idea as you're going through these. Of course, the answers are in the back of the book, but the way you type this one in, you'd be integral, int, and then you got to type in the function cosh of the square root of x divided by the square root of x. And I think that should do it. Let's see what it gives us. No, I didn't type it in quite right. I need another parenthesis here. So put a parenthesis there, and let's type it in again. There we go. Nice. So it matches what we got. Now sometimes it gives you kind of weird forms, but generally it's pretty well behaved. So it's a nice way to check some of your answers in a pinch sometimes. How are we looking on 46 there? Let's try 48. So the hyperbolic sine divided by 1 plus hyperbolic sine squared of x dx. At least the way it stands, this is not set up very nicely for a u substitution. So what can we do here? Let's see, we had an identity that I suggested that you know, right? What was it? It was cosh squared minus sinh squared equals 1. That's the one identity that I asked you that you know. Yeah. If you move this to the other side, you get cosh squared equals 1 plus sinh squared. And that's what you needed to get this thing going. So we got sinh of x, cosh squared of x, dx. And again, the reminder here, this notation really means cosh of x squared, sinh of x, dx. Did that help us out? Did rewriting that? Okay, so what would you suggest now? U substitution, good. What is u going to equal? Yeah, u is going to equal cosh, and then du is going to be sinh. So u equals cosh, du is going to be sinh I'm going to kind of fast forward that. Du is going to be sinh x dx. So that's our du over u squared. Please don't integrate that as the log. All right. How do you have to integrate this one? What would you do? Yeah, bring it up. So it's going to be u to the negative 2 du. As long as this exponent is not negative 1. If you're integrating some polynomial, you add 1 to the power, so u to the negative 1, and divide by that same power. Now, this is my suggestion, is that you just kind of take care of this business slowly. And then simplify this. The negative I can write out in front. This can come down into the denominator. And finally, that's negative 1 over Cosh of x plus c. There's actually another way that I'd accept this, and I'd actually be kind of happy to see it. Is there anyone that could write that a different way? Yeah. Hyperbolic secant, right? Just 1 over the hyperbolic cosine. I'm not going to be really picky about which one of these you give me, just as long as you get one of these. Either one's fine. Let's try one last one here. This one we're going to do on the graphing calculator. And I'll let you pick it, either 56 or 60. Which one do you want? 60? Naturally, you pick the harder one. Okay. All right, that's fine. Let's go with the harder one. So we're just going to see if we can't get a numerical value from this. Certainly, it's important to me that you be able to do that. So I'm just going to copy this down here real quick, and then we'll work together to input this into our calculator. Now with this one, unlike our one in section 5.8, it doesn't matter if you have it in radians or degrees. Cosh is not going to be affected by that. To access the numerical integration, you want the fn int. Fn int. If your operating system and your calculator is up to date, if you borrowed one of mine, or if you have a nice up-to-date operating system, then you'll be able to type it in naturally. If not, it's going to look like this. You're going to have to put in the function f of x, and then the variable x, and then the lower limit, and then the upper limit. And these will be separated with commas that you'll find right above the 7 on your calculator. Hopefully, your operating system is up to date, and we can do this just by entering that in. So I'll hit the math key, and then 9. That gives me fn int. I want to integrate from 0 to the ln of 2. So I'll just type that in, ln of 2. I want to write parenthesis to close off that 2. Probably would work without it. Arrow over here to find my way to the integrand. 2 second e to the negative x. Press the right arrow to exit from the exponent. And then I need Cosh. Remember, Cosh, you got to go to the catalog menu. So I'll hit second and then 0. I can jump down to the C's by simply pressing the program button. That'll forward me down a little bit. And then I got to do some scrolling down to Cosh. Cosh of x. And last but not least, I got to tell it what variable I'm integrating with respect to. Yay. So a little bit over 1. So approximately 1.0681. How many people were actually able to get that number? Okay. All right. I would suggest you spend a little time practicing that. And for homework, try 1 through 7, then skip a little bit up to 23 through 35. 43 through 53, and then 55 through 59. Do these on a graphing calculator, just the way we did problem number 60. Okay, here's a good place for a break. Oh no. Oh, wow. Yeah, I think some of this is not going to show up. I don't know. We'll see. But we'll give it our best.